but malaria remains a major killer. Malaria was present throughout Europe. At the end of World War I, there was a major malaria outbreak in Archangels, Russia. Refugees from the south brought the parasites with. No one is totally protected in any environment against malaria. Anopheles mosquitoes are almost ubiquitous. And in sub-Saharan Africa, this remains a major killer, particularly of the small children, youngsters like these little boys. Aren't they cute, adorable little fellows? Now, they live outside of our field station in southern Zambia. I don't know whether they have malaria or not, but they're being protected against developing malaria. And if they should develop malaria, they'll be treated aggressively. But shown here is a youngster brought in from further into the rural district, comatose, near death, with cerebral malaria. You remember a few slides back I talked about brain edema? Well, one of the manifestations of malaria is cerebral malaria, where it's a combination of brain swelling and infarct that causes brain damage. Now, the good news is the child's life was saved by Philip Tuma, a Johns Hopkins trained pediatrician who devoted his entire professional career to working with sub-Saharan Africa, in malaria hospitals, particularly that hospital in southern Zambia. So the child's life was saved, but notice he has a disconjugate gaze. He's gazing upward because he's sightless. The brain damage of the neurovisual cortex because of the malaria infection has rendered him permanently blind for life. And we think being blinded, hearing deficient, learning impaired, epileptic is a problem in Western civilization. Imagine being impaired in a third world community. So there's still much work to be done. Drug resistance has made the existing medicines less effective, and the danger is within a decade we're going to run out of medicines, and malaria will reverberate through the developed world. Presently, we're down to under 1 million deaths, but it could easily skyrocket. 1 million deaths is too many, and we consider that maybe tens of millions of children are left blind, epileptic. It's still a big problem. Now, I talked about the aquaporin spore in brain. This is just an experimental slide of a mouse brain showing what happens during cerebral malaria. And the aquaporin spore is normally present at the perivascular astroglial end foot. So here's a capillary brain. These black dots represent the presence of aquaporin spore normally. In the presence of cerebral malaria, notice the swelling, this blister-like accumulation of fluid. That's what kills the kids. Can we prevent it? No. But if we could prevent malaria, we would prevent cerebral malaria. Now this beautiful bridge represents the border of Zimbabwe and Zambia, so we're working in sub-Saharan Africa. And I show that not because it's an architectural wonder over the Zambezi River, but to point out that control in one region does not guarantee that it will be permanent, because if adjacent geographic regions don't treat malaria aggressively to eliminate it, it comes right back. The mosquitoes that carry this don't have passports. They cross the border freely. And mosquitoes also have a series of aquaporins which move fluid rapidly. You may not think about this much, but when a female mosquito bites us to take out blood as the blood meals for egg development, it's actually rapidly releasing transidates to now thinking those aquaporins are involved. The lightness wait to fly off again. We're presently working on Anopheles mosquitoes aquaporins. Not confident we'll find something with practical utility, but the basic biology could be useful. Well, I'm going to turn back to the other aquaglyceropods briefly as I close, because they play important roles as well. Particularly aquaglyceroporin 7 and aquaglyceroporin 9. 7 is present in adipose tissue, and I think we're all aware in Western societies of the new epidemic of obesity. In the United States right now, 2/3 of the adults are overweight, 1/3 are obese. Through evolution, we've developed great efficiency for storing calories because our progenitors in previous generations were threatened with starvation every winter. The individuals who can store extra calories had a survival advantage. In the aquaglycerol form 7 is the mechanism for release of glycerol from fat during fasting or starving. Glycerol being the preferred gluconeogenic substrate. It was taken up by the liver, and the aquaglycerol form 9, which is expressed heavily during fasting, will convert glycerol back to glucose. Marathon runners are keenly aware of this. This bonking phenomenon that occurs after about 2 hours is when you change from burning glycogen to burning fat. Humans who've been identified with mutations in this look normal, feel normal, but they can't release glycerol from fat. They'll never win marathons. That's not so important in modern life, but believe me, in previous centuries, it was important for survival. Another surprising function, and this is work of Jenny Carver, who's now faculty member at Duke. Science is always so surprising when someone does something a little kooky and finds something unexpected. It was Mary Rosen from Wayne State University, Michigan, who found that aquaglycerophores are freely permeated by arsenic trioxide, uncharged at neutral pH. Of course, the arsenic trioxide must chemically resemble the glycerol molecule, the carbon polyol. What does this mean? And is it important? And the answer is it's quite important because arsenic toxicity is still a model effect. In this country, well, surface water better than nuclear power. So the groundwater has high natural stores of arsenic trioxide. An epidemic of arsenic toxicity is now being experienced in that part of the world. The World Health Organization predicts 140 million people are drinking arsenic toxic water every day. And a series of studies, knockout studies with Søren Nielsen, who confirmed the fact the aquaglycerol 9 is present in the liver. Here's the null, the specific same in the wildlife models. And when they're injected with arsenic, radioactive arsenic, the normal wildlife mice can excrete the arsenic from peritoneum to the liver into the feces. The nulls cannot, and the nulls succumb earlier. So maybe that's the real explanation for why we have aquaglycerol 9 in the liver. Another explanation, I should say, so that we can detoxify arsenic. And yes, plants have numerous aquaporins. This is a slide I borrowed from Ralph Kaltenhoff from the University of Würzburg in Germany, showing the presence of aquaporin null state in the Arabidopsis, a small mustard plant. In fact, there's, I think, 35 different aquaporin genes in the Arabidopsis. Normally, this plant can maintain normal stem turgor and foliage through the thin arborization of rootlets. But the engineered strain, which underexpresses the PIP1B aquaporin family, reduces it by down-regulating the expression of the PIP1B to 20% of the wildlife level. The plant now faces an inability to take in enough water. And it compensates by sending out more rootlets. It's very simple. When the rain stops, the wildlife migrate to the next water hole. The plants stay behind. Those plants that can compete for water survive. Those that cannot compete don't survive. So there is some significant potential. And of course, these are already ongoing in a number of wild-type plants. So in closing, I'd just like to skip quickly through the talk I talked about, the free permeation of water through aquaporins, the substrate variations of some specific members of the family, the structural models, and just some of the disease states where we believe these are featured. Now, identifying the presence in a disease state is only the very beginning of the battle. The development of medicines to manipulate this information to either upregulate, mislocalize, or antagonize the water channels are potentially of therapeutic interest, maybe of great value. But to achieve this work, we need young scientists like yourselves. So I'm kind of issuing a call out here. I think we've done some easy work, it's been interesting, but the hard work, the important work, lies ahead. But returning to the topic of the Nobel Prize, I'd just like to share a little bit of the event with you. This was the morning, almost 10 years ago, when I got a call early in the morning. Because of the time difference, it was, I think, 5:30 in the morning, the phone rang. And yes, there were some clues that the Nobel Committee was interested, but nothing very convincing. So the phone rings at 5:30 in the morning, pleasant Swedish voice. This is an important telephone call from Stockholm from Professor Peter Agre. Are you Professor Agre? And I replied, why, yes, I am. And we went on to inform me that I was sharing a Nobel Prize in chemistry with Roderick McKinnon, who I knew, a medical doctor like myself, who worked on structures of potassium channels. So they went on to explain what had happened, and he said, now we're going to hang up in 10 minutes of the press conference in Stockholm. You should get ready for your day. So I sprinted to the shower. My wife, Mary, wiser, organized, calm, called my mother back in Minnesota, wakened her early in the morning to tell her the news. Her son Peter will share the Nobel Prize in chemistry. My father, who was a chemist, had died 8 years earlier. Mother thought for a moment. She said, Mary, tell Peter that's very nice, but don't let this go to his head. I think she was indicating he still needs to do something useful. I think that's an important message. But by the time I got to the laboratory, about 10:30 in the morning, the news had gone to the heads of the young people. They were on their third bottle of champagne already. And the university president came over to see me. I had no idea till that moment what close personal friends we were. Funny when the Nobel Prize would do. And shown here are the faces of the young people in the laboratory. And that morning, we had people from 8 different countries in our laboratory. And this is one of the great joys to be able to share an event like this with young people who come from around the world to work in scientific laboratories. We can make friendships which last the rest of our lives together and have a second important delivery on the investment of science.